Week 12, part 3. This is more on Snell's law. So here is a kind of a picture of some various rays that could be entering a piece of glass and bending as they do. And I've got numbers on here showing the angles. These angles are all with respect to the normal. They're always measured with respect to the normal. Sometimes those are called the incidence angle. So if a ray comes in 10 degrees from the normal, it bends a little bit and comes inside the glass, it's proceeding at 7 degrees from the normal. If it comes in at 30 degrees from the normal, that would be the angle right there. Then it bends a little bit more, and inside the glass, it's at 20 degrees from the normal, again, the incidence angle. 60 degrees bends even more, comes at 35, and 80 degrees bends all the way over to 41. So here's a chart of those angles. And you can see I've got the full range of incidence angles for phi 1, which is the angle out in the air, and phi 2 is the angle inside the glass, and it ranges all the way up, but there's kind of a limit here of about 40, almost 42 degrees. And of course, you could work this backwards. Any of these, Snell's law works both directions. So you could imagine a ray of light that is 35 degrees from normal approaching the surface, then it will bend away from the normal and bends out and comes out at 60 degrees. Or a ray at 20 comes out at 30, that sort of thing. But you might be wondering a little bit, what about rays out here that are even at a greater inclination to the surface, like something like that? If we had a ray going at a greater angle instead of down here at 41.8, what at 50 or 60, something like that? What kind of result would we get then? Well, we can do that. Let's just do that as an example. We'll try to work the problem and see what we find out. So let's start with our interface here. This is the surface, and out here is air, where n equals 1. This is glass with an n equals 1.5. And here is a ray approaching the surface at kind of a shallow angle, and we'll make that angle be 60 degrees, well beyond that limit that we were looking at before. And we'd like to know what angle will it emerge into the air. What will be its angle out here? We assume it would bend away from the normal somehow, something like this, and we'd like to get phi 2. What is that angle out there? So using Snell's law again, always, n1 sine of phi 1, and this will be in the glass to start with, and that equals n2 sine of phi 2, where 2 is now out in the air. Putting the numbers in, we would have 1.5 times the sine of 60 degrees equals 1.0 times the sine of phi 2. What is phi 2? Well, you can do the math. I'll do it for you here. It's going to be the arc sine of 1.5 sine of 60 degrees divided by 1.0. Don't really need to do that, but we can for completeness. And if you try that on your calculator, we'll go ahead and try it if you like. Spend a little time punching that away. What you should get is something like error. It won't give you an answer. And the correct answer is error. There is no solution. There is no solution to this equation up here. There's no answer. It's like asking for the square root of -3 or something like that. There is no such answer. And what that means is that there simply is no ray on the outside. The light does not come out. It does reflect. You'll get a reflected ray down this direction, but there's no ray up in the air. Now, of course, you always get reflected rays, even if you were coming up at an angle that did give a ray off at some angle like this, the examples we had before. There's also a ray that reflects down into the surface. The difference in this case is there is only a reflected ray. And so that reflected ray becomes much, much stronger. Right at the point when the other ray disappears, then this ray becomes stronger. And this whole phenomenon goes by the name of total internal reflection. And we can calculate the angle, this sort of critical angle, after which there can be no external ray. It amounts to going back to this chart and saying, how did we get this 41.8? Well, we considered what happens if the ray on the outside is at 90 degrees. That's the limiting case. Then you calculate what the angle is on the inside. So let's do that. Here again is glass and air. And if we put in N1 sine of phi 1 equals N2 sine of phi 2. So in the glass, we've got 1.5 sine of, and here is where we're going to try to find the critical angle that divides between having an external ray and not having one. And N2 out in the air is 1.0 sine, and then here we put in 90 degrees. Well, this is just 1. The sine of 90 degrees is 1. And so when you solve for this, you'll find that the critical angle is just the arc sine. In this case, it's going to be 1.0, that's this side, divided by this 1.5 over here. Let's get rid of this 1. And that, that comes out to be the 41.8 that you saw in the chart before. Writing it a little bit more generally, the critical angle is the arc sine of the index in the external material divided by the index of the internal material. So the index of the glass divided by the index, the index of the air divided by the index of the glass. There is only a critical angle for internal reflection inside the glass. When you look out in the air, there is no such phenomenon. All of these rays out here do in fact penetrate inside, but not all of the rays on the inside connect to a ray on the outside. Some of them at a greater angle are totally internally reflected. This can be seen in some interesting ways. I'll show you one common way this is used is in fiber optics. You may wonder how fiber optics works, and one of the chief things that it makes use of is this total internal reflection. So I've got a laser here, and I can shine it inside this coil of acrylic plastic, and you'll see that it emerges right there. The minute I get the laser beam inside, you can see it showing up there. It's even more dramatic if I use my phone and light the whole thing up just like that. And you can see the light is following the fiber rather nicely. What's going on is the light ray, once it enters the fiber, its angle is shallow enough, it is totally reflected inside and follows the curve around and around any which way it gets curved. Each time it reflects from the edge, it's totally internally reflected, so there isn't the loss that you might expect otherwise. There's another way you can observe this. If you go swimming, and I've got a video here I want to show you all. A student of mine created this many years ago. In 2007, David Bontrager took advantage of the fact that at that time, Goshen College had a pool. And so here is Here's the picture of the inside of the pool. Actually, I want to start this over again. See where we got. Yep, there we go. So he's starting out above the water, dipping into the water, and now you're seeing the lane markings on the bottom of the pool. And then he looks up toward the surface. And if I can stop this at the right moment, he's looking around in different directions and right about, no, that's not the best. There's an excellent one. So he is looking up with his camera. And as he looks up toward the surface of the water, you're seeing the ceiling of the pool area. This is now just what do they call it? It's in the Rec Fitness Center, the great big room. It's not the gym, but the other room that used to be the pool room. And you're seeing the ceiling of that room. These are some of the windows and stuff. And as you look down towards greater and greater angles, at this point, there's a transition, and the surface of the water has become a mirror. And essentially, all he's seeing here is the lane markings that are on the bottom of the pool. He's still looking up, but seeing those lane markings reflected in the top of the pool. And this line along here is sort of the division between where you have total internal reflection down here, and up here, you've got rays that are refracted. They're kind of distorted a little bit. Things are compressed in this direction, and then up here, not quite so much because of that bending effect. But this really shows it very clearly.